Hey friends, welcome back. In this series of videos, we will see that what is a super learning mechanism is, and many algorithm used in supervised learning and how they work. So before starting the linear regression, let's start what the super learning exactly is. As the name itself, or we can say as in terms of machine learning, super learning means building a mathematical model using data that contains both the input and the desired output, right? For example, determining if an image has a horse or not. In this, the data would include images with and without the horses, right? And for each image we would have a label, so that would be nothing but our output that will indicate if there is a horse in the image or not. Another example we can take as determining that a client might default on a loan or not, or determining if a call center employee is likely to quit or not, right? In supervised learning, we will have desired outputs, okay, or the model performance can be evaluated by all those comparisons. In the supervised learning, we have many mechanism, or we can say algorithms, like mainly there are classifications and regression methods. Uh, like in classification, we will see logistic regression, naive bias, KNN classifier, SBM classifier, etc., etc. And in regression, we mainly have linear regression, KNN regression, SBM regression, all these kind, right? So let's start with supervised learning, where we will see linear regression. Okay, so for linear regression, we basically need like there are some prerequisite that are statistics, or we can say another module that is exploratory data analysis, that is EDA, right? Because like mean, median, mode, variance, standard deviation, correlation, covariance all falls under statistics, and like data distribution, scatter plots, correlation matrix, heat map, etc. These are falls into exploratory data analysis, right? The main objective for this series is to understand what is linear regression and motivation behind linear regression, right? So if we talk about particularly linear regression, okay, basically that is a way to identify a relationship between two or more variables, and use these relationship to predict values for one variable that might be given values, right, of any other particular values. So linear regression basically assume the that relationship between variables that can be modeled through linear equations or in equation offline. So by the linear equation, against we go back in our mathematics, where we have y equals to c plus mx, right? So we will implement this equation with our linear. So we will implement this equation with our linear regression model. Now let's start with this particular example with linear regression, where we will construct a linear model that explain the relationship with a car's mileage, that is in MPG, that has its own attributes, right? So again, starting with the importing libraries, NumPy linear regression that we import from sklearn. Okay, in sklearn we have linear model, so we import linear regression from that. Pandas, matplotlib, all these for better visualization. And this is our main thing, that we will use our sklearn package, that is for randomized data splitting function. So here we can split our data into testing set and training set, right? So let's import the data set that will be provided in the description as well. If we talk about the shape, that is the 398 by 9, that means there are 398 rows, or we can say data set of 398, and 9 attribute are there. If we print the head, so you can see that this is the head that we will have, all right, and this is the bit description about the data set that we are gonna use. And here what we are doing is again we are dropping or ignoring car name, because we will take only those parameters that are required for the linear regression perspective. So what I'm doing is I'm dropping car name, and from axis axis 1, so the particular column will be deleted, and also replacing the categorical variable with actual values, right? So where there is a column that is origin, okay, so in origin we are telling that okay, replace 1 if America, replace to 2 if there is Europe, and again fill 3 or replace 3 with Asia, so that will be replaced accordingly. All right, again we check the head, so we will get the values. So here you can see that all the origin have been upgraded. Now we are gonna create dummy variables. So what about dummy variables? Basically these are the values like America that cannot be read into an equations. Okay, so using some attribute like 1 for America, 2 for Europe, and 3 for Asia would end up implying that European cars fall exactly halfway between American and Asian cars, right? So we don't want to impose such a baseless assumption. So we create three simple true or false column, right, with titles equivalent, that is this car America, or is this car European, or is this car Asian, right? So again in C data we are getting dummies, right, of that particular origin, and then we are printing that. So here you can see that origin for America, origin for Asia, origin for Europe. So if that is America, so America will be 1, if Asia, that will be 1, rest will be 0, and if it is from Europe, so that will be 1, rest will be 0. Now dealing with missing values, again first taking the 5-point summary or the describe function, so that will give me the insight description about my data, right? And what I'm doing is here you can see that these are the data type, right, that we have. So what it is telling that HP is missing because it does not seem to be recognized as a numerical column. So I hope this is talking about this particular description, right? So now what we are doing is we are checking that if the string is made of digits, right? So store true or false in that case. Okay, so c dot horse for string dot is digit, so that will basically return true or false if that is in the string that is made of digit score. Now what again we are doing is we are telling that from this particular temp, okay, just take only those rows where HP has false. So if the horsepower, that is our HP, is false, so only take that in HP is digit, right? So in that particular variables. Now we are checking missing values that have a question mark, right, or replace missing values with none. So what we'll do is we can see that as these are the horsepower which containing question mark, so np.none will replace that with none, right? And is digit horsepower, again we are doing the same thing if that is false. So there are various ways to handle missing values, as I have already discussed it with you. Please find those video in the playlist, right? So drop the row, replace column values with median value, etc, etc. There are many methods to do that of the these particular attributes. So they have none in the HP column, so we could drop these 6 rows, right, which have a none values, and which might not be good idea under all situations, because other attribute might be useful with some cases, right? But we cannot say all the time that okay, this particular attribute contains none, so just drop those values or all those rows, right? So that is not the case. So instead of dropping this row, let's replace the missing value with a median value. That is a again perfect idea, or we can say we can impute the values in that way. So now what I'm doing is I'm getting the median here, right? So replacing the missing values with median value. Okay, so note that we do not need to specify the column names below. Exactly. So every column's missing value is replaced with that column's median respectively, right? So if axis is 0, mean column wise. So here see data, like how will it work? You can see the example here, but before that what we are getting is we are getting the median filter, right? So by performing that anonymous function lambda, right? And we are telling that okay, just fill NA with that particular median of that attribute. Now we are getting the data and we are telling that just apply this median filter inside our original data set, right? For all those rows. So here we are storing the horsepower as float type, right? Or we can say we are converting our HP column from object to float. So let's start with some analysis. So again, with the starting with the bivariate plot. So a bivariate analysis among the different variable can be done using a scatter matrix plot. Seaborn Libraries creates a dashboard reflecting useful information about the dimensions, right? So the result can be stored as a PNG file. Okay. So here again for those attribute we are getting ilog values, right? And ilog will get the particular column and the value that we are trying to get that index, right? So in pair plot we are telling that okay, just plot a pair plot for these values and the diagonal is true. So here just we are trying to plot the density curve instead of those histogram on the diagonal, right? So that is diagonal kind. So here you can see that this is the pair plot for all these values, and the observation here it is telling that between MPG and other attribute indicate the relationship is not really linear. So let's see where the MPG, right, and with other attributes. So if we check MPG with so here you can see that with cylinder, with displacement, with horsepower. So the curve you can see that, or the relationship that is not really linear. However, the plot also indicate the linearity would still capture quite a bit of useful information pattern, right? So several assumption of classical linear regression seems to be violated. Okay, so including the assumption of number of heteroscedastic, right? So let's split the data, okay, for our training and testing purpose. So what we are gonna do is building our linear model first with independent variable. So in the X we are telling that just drop MPG and origin euro. All right, so that will be dropped permanently, and rest will be stored in our X. For the Y, we are just telling that okay, just give me the MPG in that Y variable. So splitting X and Y into training and test set in the 70 and 30 ratio, right? So for each. So here you can see that what we define is just only 30% or 30% of the data set is for testing purpose, right? So here x train, x test, y train, y test. So here we are getting it from linear regression, that is train test split we have imported initially, right? So here you can see that train test split from the model selection. Now as we have defined our ratio as well, right? We just pass the test size and we just pass the test size, so training is automatically known. Now we are fitting the linear model. Okay, so what we call is we have the linear regression function that we define and we are storing it into regression model. Okay, now in the regression model dot fit we pass that x train and y train. Okay, so here our model will get prepared. So here the coefficient for each variable and the intercept will be assigned. Now to do that, here we can see that we will get the coefficient for all the attributes, right? So for cylinders, displacement, horsepower, weight, replacement, so everything will be here from these extreme values, right? And from where we get it into a regression model dot coefficient. Now just take the intercept, right? So regression model dot intercept, we are taking that, right, which is at initial position, and printing the intercept for our model, that is this particular format. We can also get the R square score, right, from the simple and out simple. So regression model dot score for X train Y train. So this is the R square score that we are getting, and out of sample score, that R square. So again for that regression model dot score X test Y test, right, that is for out of a sample, and for in sample, right, it is X train Y train. Now adding interaction terms, so what that means is basically we trying to add those interaction terms between train test and test set, right? So again we are importing our polynomial feature from pre-processing, right, and linear model from sklearn, and we are telling that in that polynomial feature, just that is of 2 degree, right, and intersection only is true. So here for our X train 2 and Y train 2, which will have the value for fit transform of X train, and it will have fit transform value for X test, right? Similarly, we will get the poly CLF, that is again linear model regression function, right? And here in that particular function, we are trying to fit our newly transformed value, that is X train, and again our old Y train. So if we get the prediction, right, so again we just call the predictive function and pass the X test to, right? So this is the prediction from testing set. So in sample training, or R square, that will always improve the number of variables. Okay, so here if we get the poly CLF score, so it will return me the improved values. And if we talk about out of sample, that is testing for R square, so that is basically our measure of success, and that also does the improvement, right? Like in printf we can get that X test 2 with the Y test, right? So that is for off sample, right? But this improve at the cost of 29 extra variable. Okay, so because you can see that if our we get the train shape for X train, so that is 278 by 8, but whereas if we get the train 2, that is nothing but our interaction terms, or we can say that we got from fitting the transform of X train. So that is returning me 278 by 37. So basically polynomial feature with only interaction terms have improved out of sample R square. So however, at the cost of increasing the number of variable is significant. Yeah, again we will come up with all the topics of supervised learning and all other terms of the artificial intelligence. So be tuned. Thanks.